We've seen that after the main sequence, low-mass stars turn into giants before gradually blowing off their outer layers to produce planetary nebulae with white dwarfs at their center. This is what will happen to the Sun after it runs out of hydrogen fuel in its core in several billion years. However, stars with 8 times the Sun's mass or more come to a more spectacular end, producing tremendous explosions that literally change the chemistry of the galaxy. They also leave behind neutron stars, which are far denser and stranger objects than white dwarfs. So let's look at the short, dramatic end to the lives of high-mass stars. Stars with initial masses between 8 and 25 solar masses are considered high-mass stars. They go through a similar set of steps in their evolution as low-mass stars, until they reach the point where the core has finished fusing helium into carbon and oxygen. At this point, in low-mass stars, core fusion stops because the core can't get hot enough for carbon fusion.
However, in high-mass stars, the temperature does get hot enough for carbon fusion, and this marks the beginning of a series of heavy element fusion reactions. So we see a repetition of the pattern we saw with helium fusion. The core contracts until it gets hot enough for carbon fusion. Then when carbon fusion stops, the core contracts again until it gets hot enough for oxygen fusion. This process keeps repeating itself for heavier and heavier elements. In these pictures, you can see some of the types of nuclear fusion that can occur, continuing up to silicon fusion, which produces iron. As we'll see later, this silicon fusion is the last stage in core nuclear fusion reactions.
One important characteristic of these heavy element fusion reactions is that each one releases less energy than the previous one. So the star runs through fusion of the entire core in a much shorter time. While high-mass star main sequence lifetimes are typically tens of millions of years, the time spent from carbon fusion onward can take as little as a few thousand years. When a high-mass star leaves the main sequence, it's luminous enough to move into the supergiant branch of the HR diagram rather than the giant branch. As it goes through successive levels of nuclear fusion in the core, it oscillates back and forth at a fairly constant luminosity, with just the temperature and radius changing as it switches between core fusion and core contraction.
Meanwhile, each time the core contracts, a new level of shell fusion starts up inside the star. This creates what is called an onion skin structure inside the star, with several different shells of nuclear fusion. There will be hydrogen fusion in the outermost layer, followed by helium fusion, then carbon, etc. Each of these layers is fusing the ash left over from the process in the layer above. The final, innermost layer of fusion is silicon fusing into iron. The next step in a star's life happens in this iron core. Here's another pair of stars to look at. This time they are in a binary system, so you know they formed at the same time. They're the same brightness, but different colors. What can you say about the masses of these two stars? You'll need to take several steps here. First, use the colors and brightnesses to determine what kind of a star the red one is. Then decide what this means about where they are in their evolution. Since mass drives evolution, you should then be able to say something about their masses.
An iron core creates a problem for a supergiant star. When the core of iron reaches a mass of 1.4 solar masses, it starts to contract in on itself. Normally, this contraction would start a new level of fusion to support the core against gravity.
But iron fusion doesn't produce any energy. When iron is fused into heavier elements, energy has to be put in rather than coming out. This is because of how the atomic nuclei are formed, and we'd need a nuclear physics course to follow this idea much further. The important consequence, though, is that iron fusion doesn't stop the collapse. and can even speed it up. In the meantime, the core temperature moves up to 1 billion Kelvin. At this high temperature, the thermal radiation produced is at gamma ray energies, so the photons have enough energy that they can start to break apart the iron nuclei.
Finally, at the extreme temperatures and pressures in the core, a new kind of nuclear reaction starts, in which electrons and protons combine to produce neutrons and neutrinos. In just a fraction of a second, the entire mass of the core is converted into neutrons, and the core collapses in on itself. The collapse continues until the core has reached neutron degeneracy, where the neutrons have been squeezed as tightly together as possible. Since neutrons don't have an electric charge, they can get much closer to each other than electrons can. So the entire core of the star collapses down to just 10 kilometers diameter. Once the iron core of a supergiant star collapses to a dense ball of neutrons, it bounces, sending a shockwave back up through the rest of the star. This shockwave destroys the rest of the star, blasting most of the star's mass out into space and creating an explosion we call a supernova. A supernova explosion expands outward away from the star at 1/10 the speed of light. For a short time, the supernova becomes the brightest thing in the galaxy. In the upper left part of the screen, the arrow points toward a supernova explosion. This particular one was in a neighboring galaxy, the Large Magellanic Cloud, which is several thousand times farther away than the foreground stars in the picture. Nonetheless, this explosion was bright enough to be seen with the naked eye from Earth.
Even though this explosion is incredibly bright, most of the energy is not released as visible light. Instead, it comes out in the motion of the neutrinos created during the collapse. Remember that throughout the core of the star, protons and electrons were combined into neutrons and neutrinos. As a result, there's a neutrino produced for each proton that was in the core when the collapse began. That means around 10 to the 57th total neutrinos are released in this explosion. In fact, astronomers have detected neutrinos from a supernova explosion, one that happened 150,000 light-years away, though they've only done so once, making this rare compared to our ongoing detection of solar neutrinos.
Finally, a cloud of gas expands out from the star and remains visible for thousands of years, though it fades tremendously after the first couple of weeks. This picture shows a supernova that was seen on Earth over 900 years ago. We call this the Crab Nebula, and we can still measure its expansion into space today.
We use the term nucleosynthesis to describe the creation of chemical elements from other chemical elements. As we've already seen, nuclear fusion in stars is an important form of nucleosynthesis. Over the life of a star, hydrogen is converted into heavier elements like helium and carbon. In higher mass stars, it's converted into much heavier elements like silicon and iron.
These elements are then ejected back into space during the planetary nebula phase of a low-mass star's life, or the supernova phase of a high-mass star. Supernovas also create new elements. The force of the explosion itself throws atoms together with so much energy that they quickly build up to form the entire periodic table. All of the remaining elements that aren't produced in normal nuclear fusion are created this way. That's the only natural way we know of to form the elements heavier than iron.
This helps explain something we noticed earlier. As we go down the periodic table, heavy elements become much rarer than light elements. After hydrogen and helium, the most common elements are the ones created by low-mass stars during nuclear fusion. The next most abundant ones are the elements created by high-mass stars during fusion. Finally, the least abundant elements are the ones produced in the violence of a supernova explosion. We've seen what happens to most of the star, but what about the core? Remember that this part of the star was converted entirely into a tiny ball of neutrons. After the rest of the explosion, this dense clump of degenerate neutrons is what we call a neutron star.
A neutron star can have a mass between 1.4 and 3 solar masses. Remember that this is the final mass. The starting mass for the star was between 8 and 25 solar masses, so the vast majority of the star is blown away in the supernova explosion. The lower mass limit is the minimum size needed for the core collapse to start. The upper limit is the maximum mass that can be supported by degenerate neutrons. We'll have to look at general relativity to see what happens beyond this mass.
A neutron star has a density of 10 to the 15th grams per cubic centimeter. This is similar to the density of an atomic nucleus. So in a sense, a neutron star is like the nucleus of a very large atom, an atom with an atomic mass of about 10 to the 57th atomic mass units. The radius is only 10 kilometers, about the size of a city. Think about how tiny that is compared to the star from which it formed.
When the core of a star collapses, any spin the star had is tremendously amplified. This is generally true with any spinning body. If it contracts in on itself, it spins faster. We call this the conservation of angular momentum, and we've seen it in action once already when we looked at the formation of disks around protostars. In the case of the core of a giant star, the collapse spins the star up until it's spinning as fast as 1,000 times a second. This is fast enough that it's near the breakup speed for the star. Any faster, and the spin would tear it apart.
The first observed neutron stars were pulsars. Pulsars were first noticed as regularly flashing points of light in the sky, with periods of a few seconds or less. They could be seen as a visible light or in radio waves, and they were often found in the centers of supernova remnants. After some early false starts, including a tongue-in-cheek suggestion that they were alien signals, astronomers recognized that pulsars were rapidly spinning neutron stars.
Neutron stars have very strong magnetic fields. Just like with spin, the magnetic field trapped in the core of the supergiant star gets amplified as it collapses. In this model of a pulsar, the field lines are the curved lines surrounding the neutron star. A strong magnetic field generates a kind of light known as synchrotron radiation. This is caused by electrons spinning at close to the speed of light around the magnetic field lines.
This synchrotron light comes out in a beam from the star's magnetic poles. If these poles aren't lined up with the pole of a neutron star's spin, then the beams of light will sweep around the sky like a couple of lighthouse beams. We then see this light as a flash whenever the beam happens to sweep past us. You can see what this light looks like in the lower right. That repeating flash is the light from the Vela pulsar, though it's been slowed down dramatically so that you can see the individual pulses.
In the decades we've been observing pulsars, we've seen that they slow down over time. It's reasonable to ask where the pulsar's kinetic energy is going.
In fact, we can see where the energy goes. It's turned into light. The glow of the pulsar and the nebula around it is powered by the slowdown of the pulsar's spin. The pulsar's magnetic field transfers the star's kinetic energy to the surrounding gas, and this creates the glow. So the energy lost from the pulsar equals the light energy emitted. Much of the light in this supernova remnant comes from the pulsar at its center.
When a pulsar slows down to the point that it takes more than 5 seconds to spin once, it becomes too faint to see. A neutron star is itself very faint. Remember that it's very small, so even though it's hot, there's very little surface area to emit light. So only a few neutron stars have been seen that aren't pulsars, even though we expect that there are many millions of them in our galaxy.
We've looked at 2 of the 3 major types of stellar corpses. So here's a making sense table for you to fill in to help you organize what we know about each. Save the last column, and you can fill that in when we finish this chapter.